Alright, so looking at today's do now, we have a student that's playing a game on a spinner, and they're using one of the spinners below, and they have the results for the 15 spins. We were trying to figure out which of the spinners the student used, and then asked us to give a reasoning for that. So when I look through this, I know that some of the spinners have different things going on here, and I noticed like the big difference is the relationship between the sizes of the different things. So on this one, I would expect to see a lot more threes down here because the space for threes is a lot bigger. I mean, that's starting to draw that link between theoretical probability here and the observational probability. Here I would expect to see the most ones. And on this one, I would expect to see that everything's probably going to be about the same. So let's go ahead and look through this. And I'm just going to tally up what my totals are. So I'm going to make a table 1, 2, and 3. And my outcomes. The number of times I got it. So I have 1, 2, 3, 4, 5, 6 ones. And in terms of my twos, I have 1, 2, 3, 4, 5, 6 twos, and 1, 2, 3 threes. So I'm looking at this and I'm thinking about, well, which one of these makes the most sense? So it definitely doesn't look like everything's even. So I'm going to rule out this one, and it definitely does not look like there are significantly more threes than anything else. So it leaves me with this one where it looks like there would be the most ones, then twos, and then threes. And we know with observational probability it's not going to come out perfect, especially in a small sample size. So we have a relatively small sample size here in that it's 15, and so we would expect some variation. So the fact that my ones and twos are about the same and my threes are not, I would guess that he's probably using spinner B, just because we can see that the threes are less than everything else, and this is the only spinner where the threes are less than everything else. And the 1 and the 2 are close enough that it would be reasonable, I think, that the both of them would have the same amount. Alright, so that's kind of starting to draw that bridge between observational probability and theoretical probability from what we can see in the spinners. Looking at for today's aim, Kipsters will be able to define a sample space and determine probability of an event. So we're just going to put it like that. Determine probability. All right. So looking at this, the first thing we're talking about is Jamal, who's a 7th grader, wants to design a game that involves tossing a paper cup. Jamal tosses a paper cup 5 times and then records the outcome of each toss. An outcome in this is the result of a single trial of an experiment. So every chance experiment has a single outcome. Jamal noted on the paper cup that it landed one of 3 ways on its side: its right side, right side up, or upside down. So we can see the 3 examples of that here. So this would be on its side, right or upside down, and right side up. And we see that it also repeated. So what we can see is that when we're listing sample space, which is what we're talking about here, when we list all of the possible outcomes, is the set of all possible outcomes for an experiment, we're only going to list the sample space as each possible outcome. We're not going to be counting at this point how many there are. So when we're talking about sample space, we're literally talking about what could possibly happen. So for another example, when we're flipping a coin, our sample space is heads or tails. Those are the 2 possible outcomes. If we have a bag of colored cubes that has red cubes, blue cubes, yellow cubes, and green cubes, our sample space is red, blue, yellow, or green. So sample space is quite clearly the set of all possible outcomes. Alright, so when we come over here And today we're only talking about single events. And moving forward, we're actually going to talk about what we call compound events, where the sample space is going to get a little bit more complicated. But for single events, it's pretty clear. Go ahead and go through questions 1 through 6 and list the sample space for each of these. List the sample space for each of these chance experiments. Alright, so looking at this first one, drawing a colored cube from a bag with green, red, blue, or black. So our sample space is green, red, blue, or black. Tossing an empty soup can to see how it lands. Well, it can land on its top, it can land on its bottom, or it can land on its side. Alright, shooting a free throw in a basketball game. Well, your choices are you can, on a very basic level, you could make or you could miss. Rolling a number cube with the numbers 1 through 6. So your sample space is you can roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, you could roll a 6. Selecting a letter from the word probability. Alright, so I could get a P, an R, an O, a B, an A, and I've already got B in there, so I don't need to add that to my sample space again. And I and L, I've already got the I, so I don't need to add that to my sample space again. A T and a Y. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of our sample space. And spinning on this spinner, it looks like our sample space, I see the numbers 1, 2, 3, 4, 5, 6, 7, and 8. So our sample space is 1, 2, 3, 4, 5, 6, 7, and 8. Alright, so that's just a brief introduction to sample space, and that's the sample space for a single event. We're going to be, again, moving forward, and this is going to get a little bit more complicated when we talk about compound events, or maybe doing multiple events together. Alright? So let's flip on over and look at the other side now. On the other side here, we're going to be starting with doing our own chance experiment, and we're going to repeat the experiment 30 times. It's actually the exact same experiment that we talked about Jamal doing at the front side of this work, where he tossed a paper cup to figure out how it was going to land. When we think about this as a chance occurrence, do you think that this is actually going to have the same chance of occurring, each of the 3 outcomes, whether it lands on its side, right side up, or upside down? What do you think? Discuss that with your partner before you move forward. So if you did think that all 3 have the same, then they're likely to occur, and so it would be similar to a spinner that looks vaguely like this, where we would expect that all 3 things would be likely to occur. If you don't think that they are also, this would be thinking about this as up, side, and this would be down. If you don't think that they're all equally likely to occur, then maybe it would look more like a spinner like this, where maybe one of them was one or the other, this, that. So let's see what really happens now that you've made some predictions. You've all been given a paper cup to toss. You're going to toss it 30 times and record your results. So if you toss it and it lands on its side, put side, or if it lands on, I guess I'm going to call them top and bottom, lands on its top, lands on its bottom, whatever it is for you guys. So obviously these are not your first tosses. You'll have to do your own experimentation to figure out what you actually get. Alright, so go ahead and toss your cup 30 times and write down all of the outcomes. Alright, so now that you've gathered all of your data from all of your observations of your chance experiments, we're going to use this observed probability to answer a handful of questions over here on the right hand side. This is all a lot of review from yesterday, so you should be able to kind of do this on your own. The first thing that I'm going to do before I answer any of these questions, I'm actually just going to go ahead and make the table to tell me how many times, or my frequency table, to tell me how many times I got each outcome. And that's just going to help me with the next 3 questions. So I would suggest that you go ahead and do that before you do any of your questions here. So I'm going to do mine. Then I'm going to answer the 8 questions, questions 8 through 11. And then we'll go ahead and check in really quickly after that, just to make sure that you are on the right track. If you want to check in after the first one, you can. But know that your answers are going to be different than mine because your outcomes are different than mine. So your observed probability, which we've talked about, observed probability is different than theoretical probability in that it's not always going to be exactly the same based on each set of observations. It should be close, and it should be an estimate, assuming that you did the experiment and the similar probabilities. So go ahead and complete this and then check in. So after creating my frequency table, I see that of my 30 tosses, 24 were on the side, 3 were on the top, and 3 were on the bottom. So when I'm calculating my estimated probability, remember we're talking about the occurrences over our total observations. Or you can think about it as Q is equal to percent times whole, where whole is our total observations 30, quantity is what we're looking for. In this case, we're talking about our side is 24, so we have 24 occurrences of the side, and we had 30 total observations, and so we want to go ahead and calculate that out. And it's the same thing as solving this Q equals percent times whole. We're going to see that we're going to get 24 over 30 either way. And this is going to give me 0.8 or 80%. Looking at the next one, estimated for probability for people landing upside down. So for me, that's the same thing as it landing on its top. So again, our occurrences in this particular case over our total observations. Again, you can use the Q equals percent times whole equation too. 3 over 24. Sorry, my total observations is 30. Total observations is 30 total observations. And so that's 0.1 or 10%. And we actually have the same probability of the cup landing right side up for me. And again, remember, your data is going to be different based on your table, but your total observations are definitely going to be the same because we all should have done 30 chance experiments here. And my occurrences for this was 3, which was also 0.1 or 10%. Based on our results, do we think all 3 outcomes are equally likely to occur? You should have answered this question. No, they are not equally likely to occur. It doesn't seem like it's even close. So I could not suggest that they are going to be equally likely to occur. Now, had it been close, something like 35%, 40%, and 30%, it's possible that could be equally likely to occur, and that it was just the random variance of our set of observations. But this is not even close. So based on my results, I would say no, this is not likely to occur. No, the difference in outcomes is too great. Is too great. All right. Now coming over here, it says use the spinner. Below, it's actually above. Oops. use the spinner to answer the following questions. So this is now moving kind of back towards theoretical probability because we're seeing a spinner and we're going to have to make some predictions about it. Now, here when it's talking about equally likely, it's comparing two specific events. It's not saying equally likely to the whole, okay? So make sure that you're being careful as you're looking at that. Are the events of spinning and landing on a 1 or 2 equally likely to occur? Actually, I want you guys to go ahead and I think you should be able to answer questions A, B, and C all on your own. So are 1 and 2 equally likely to occur? So I'm comparing 1 and 2, and what I can see is that they seem to have the same portion of the spinner, which would suggest to me that they would be equally likely to occur. They're both 1/4. And I would expect that since this is random where the spinner is going to land, that this would probably be about 25% of the time it would land on 1 or 2. So I would say yes. Are spinning 2 and 3. So that's comparing 2 and 3. What I can see is there's a lot more space for the spinner to land on 3 than there is on 2. And so I would say no, they're not equally likely to spin that way. And actually, if I start to think about it in terms of my theoretical probabilities, this looks like this takes up about half of it. So I would expect this would be about 50% of the time. This would be about 25% of the time. And this would also be like 25% of the time. So how many times would I predict the spinner will land on each section after 100 spins? Well, this is after 100 spins. We can think about each of them as Q is equal to percent times whole. And we've just come up with some percents there. So we would expect 25% of the time for A. So this is A. No, not A. 1 times 100 would be 25 times we would expect. For 2, Q is equal to percent times whole. And I got, yeah, so, and our 2 also has a 25%, 0.25, according to our quick look, times 100 is going to be 25%. Or no, not 25%, 25 times. And 3, we said, looks like it has a 50% chance. So, again, Q is equal to percent times whole. So it's 0.5 times the whole, 100 times. And that's going to give me 50 times. All right. Draw a spinner that has 3 sections that are equally likely to occur. And then how many times do you think the spinner will land on each section after 100 spins? So go ahead and jump through this question and answer the question before you move forward. All right, I drew a spinner like this earlier today for you guys. We are looking at, it should look like it is cut into 3s, which is that kind of Y shape. Kind of looks like a peace sign. 1, 2, and 3 would be equally likely to occur. And if we're looking at how long the spinner would land on each, well, each of these would be 1/3 or 0.3 repeating or 33%. So if we thought about it, each of them would be 0.33 repeating times the whole, which is 100. Should be approximately, again, if we're rounding here, 33. So we would expect it to be right around 33. Obviously, if we had 33, 33, and 33, that's going to give me 99, and there'd be one more spin. So we'd expect that theoretically we'd be looking at 33 or 34 times for each spin. All right. So go ahead and flip on over to your alone time and